So hi everyone, this is my numerical methods project and I did this all in Java, NetBeans, Apache version 21. So you have here the start button and you have here the methods. So let's start with incremental search method. We're gonna put lower limit of -1 and 3 for the upper limit. And let's choose the equation sin x minus 0.5. We'll have a more precise tolerance or delta. Of course, we have here the need help button still. For the users that don't understand, they can just read this. And now we see here the function plot. We have two roots. And we have here the corresponding table for the incremental search method. Now let's try another method. So let's try bisection method. How about we have something different? Sin x minus 0.5. Let's try. Oh, sorry. The equation goes here. Let's try 1 for lower limit and 3. Let's still assume it's in there. Let's try 0.001. I'm not sure about that, but let's try bigger iteration 200. So have here the need help button, and let's try that. As you can see, there it is. How about let's try in the graphical method. Oops, accidentally. Oh no, not graphical. Okay, whatever. Sin x minus 0.5 to 20, 200. Oh no, look at that. Anyway, let's try. I think I'm gonna try second. Nope. Let's try Newton. Regular false. Sure. And let's try something that has another multiple root. Let's try sin x minus 0.5 again and lower bound 1, 3. We'll have the iteration, a max iteration of 200. Still have here the need help button. Actually, of course, for those users that do not know, can read that. Okay, go. So you can see here, here's the corresponding table, and here's the root. So for you guys that do not know, I use JFreeChart and JConjar and XP4J for all of these. So I really hope that you tag along. Let's try again. Oh, sorry, my let's delete. X cubed minus 4x minus 9. Let's try 1 and 3 again, or let's try 2. 0.001. You have here the need help button, of course, for the legend. And of course, it also tells here that the red dots are the second iterates, and this is the root approximation. Still the same, 2.7, which is correct. So when you're making your program, guys, you gotta check the equations, of course, the answers and stuff like that. So how about we talk about the code? Let's try talking about bisection while we're at here. So as you can see, this is my JFrame form. It's very simple. These with their corresponding variable names. And then you can parse it in here in the enter button. This is where it all goes. So basically my bisection method is this is my core logic. This is my core logic, the bisection solver, which actually holds the formula, everything, how it solves. It takes an equation, a string, the tolerance a string, and the max iteration is string. So it's still connected here. in the equation evaluator, which is here. This is it. So basically, it computes the function values dynamically. So this is why we can solve multiple roots and stuff like that. This is also the design for my graph. Basically, it records each interval bounds, midpoint, function values, and error. So you can see we have here the private void check subinterval roots, private void find root, and the other ones, which brings it all together. It supports checking subintervals for additional roots by recursively applying bisection. Returns both the iteration and it also not just the iteration but also the root list for plotting, which we have here in bigraph, the public void graph. I'm sorry, public void display results. We have here the table that we need. This is what you saw when I tried to run it, and then the absolute error. We have here the hundreds places, which was the requirement. Next is the bisection method GUI. You have seen this, right? Here are the text fields that you need. It's actually easier I think, when you do this in something that runs on an application like NetBeans. So basically, the user interface for inputting parameters lower limit, upper limit, equation, and delta, or tolerance, and max iteration. So it includes a custom numpad of function buttons like the trigonometric function in cos. So basically, guys, when you enter this button, it invokes the bisection solver to compute what it just parsed. So you see here string lower text. It gets in the text fields that I just showed you. It works with all my methods. So yeah. So let's move on to another one. Let's not get too dumbfounded by that. We have here the second method. Oops. This is the graph. I have made a different graphing table for each one, just to have the title here so that you won't. Yeah, I'm missing a T there. I'm sorry about that. So we have here the second method. So basically, this is the GUI for the second. We have here the text fields, the buttons. So we have here the need help button too. This is what shows up. Anyway, so the input window where users enter the initial guess or x sub 0, and the function equation a string equation f, which I named text field, and step size or tolerance or step size f. So these custom numeric and function buttons append characters at caret in the currently focused text field for easy input. So if you're asking, this is what I mean. So that when you tap on this button or click it, it just shows up on all the text fields. That's why I set it to active field and not to a specific text field, which you can do, but that would be in a future improvement of the application. The second solver, of course, uses the equation, the formula xn plus 1 equals x sub n minus the function of x sub n, and then multiply by x sub n minus x sub n minus 1 over the function of x sub n minus f, the function of x sub n minus 1. And that's all you need for the second method. Next is the Newton-Raphson method. So the Newton-Raphson method, as you can see, this is my GUI. Still the same buttons. The text, the input fields for each method, of course, is different. For the Newton-Raphson, we need the derivative. So the user input has the function of x, the derivative or of f prime of x, and the initial guess, which is x sub 0, and the tolerance for stopping criteria. So this supports the same numpad and functions, just as input. So on enter, it parses the input, instantiates Newton solver, You have your Newton solver. This is Newton solver, guys, which holds the core logic of our Newton Raphson method. So it instantiates Newton solver and calls solve Newton, which we have here, solve Newton, and that passes to the end graph. So this is where our table shows up and our plot. So next is, let's get to graphical method. Let's go there. So this is something that I was really embarrassed about because I don't know if this is correct. This is by far what I've heard is the simplest method, but I really overcomplicated things and I hope this is correct. But for my explanation, for my understanding, this is my needed text fields or inputs for the user. So the enter button still triggers the root finding process. It reads the input, calls graphical solver, and with the function string and max duration and resultant instances. So it ups. So basically, guys, with the graphic solver, it passes it to iGraph, which is of course again, you can see, is the incremental search graph and table. Very simple. Basically, it updates the result window label with the number of roots found, and then this JTable and JPanel displays the plot chart and the sample x values and corresponding function of x, and a label showing number of roots found. It has, of course, I forgot to show you the main menu, which takes us back to the choices. It is so simple. Basically, it's, yep. So basically, guys, the last method that I'm about to show you is regular falsi. So regular falsi is known as false position method. So we still have here. This is my text field for this one. So we have here the equation f for function of x, lower bracket is x sub L, and upper bracket is x sub U, and the max iteration field is obviously the max number of iterations. So we're gonna go to regular solver, which is the core numerical solver logic. So this parses the user equation right from the enter button. So we know that the formula to iteratively compute new root approximation of x for x sub r with formula xr equals x upper bracket minus the function of the x upper bracket times x lower bracket minus x upper bracket over the function of x sub l minus the function of x sub u or upper bracket and lower bracket. So that calculates the approximate relative error, and it's in percent. It updates the bracket based on sign of x of the function of lower bracket and multiplied by the xr, the function of xr. And so it stops its function, basically, guys, stops its function value at root or error is below threshold. So basically, guys, that's my numerical methods in NetBeans. Thank you.
For applying this in Python, you implement these numerical root finding methods by being more concise and flexible thanks to Python's dynamic and rich standard libraries such as NumPy, SymPy, and Matplotlib. So for function handling, like for what I use in Java, which is XP4J, Python offers multiple ways to handle mathematical functions such as using lambda functions or regular Python functions for defining the function of x or f of x. So for MATLAB, first we create the main figure using UI figure, setting a custom window, title, and size. We also add a sidebar panel for method selection and control buttons. So for everyone that doesn't know, MATLAB stands for Matrix Laboratory. So that means it's a high-level programming environment developed by MathWorks. It's widely used in engineering, math, physics, and data science for tasks like solving mathematical problems, visualizing data, and simulating systems. So as you can see, as we run the MATLAB program using MATLAB syntax, we have the graphical, the bisection, second, heater, absent, regular fallacy, and incremental search as you try to run it. So for tips, you can just convert your um, own language made calculator into MATLAB syntax, or try to study it to convert it well.
We are about to try out for both singular root and multiple roots. So we have here incremental search methods. So we have here a need help button in case if a user does not know what to do and what all these input text fields mean. So let's try out the equation x cubed minus 4x minus 9. So we're going to assume that the lower limit will be, let's say 1, and the upper limit will be 3. So let's assume it's in between that. So we'll have the delta or step size. So we'll have 0.01. And let's see if we get the root 2.7 estimate. So I have here, this is the root. We can zoom in on that, and you can see that it is bound here. We have here the corresponding table that goes with the graph. As you can see, we'll try a multiple root in the incremental search method. Let's try x cubed let's say minus 6x squared, or yes, let's try that, plus 8x. We have, let's assume it's negative 1. And let's assume we have the upper limit of 5, so we're gonna, I think it's in between that. We'll have a step size of something bigger, 0.1. Okay, so now we have here 3 roots, still with a table. So you can see here, it says here root bracketed. Let's expand it, bracket. And another one here, root bracket in 1.9, which is this one. You can zoom in to find out